card. There you go. Okay, I don't know where Mr. Brian Smith is, and a little concerned with Matthew not coming to the class. I mean, he's been submitting his assignment, so I hope he's doing okay. And maybe it's just his choice that he feels that not attending the lecture is helping him and saving him some time. I'm perfectly fine because he's fulfilling his commitments. So I hope everything is okay and going well with him. But Brian is usually here, and I hope he's doing well too. But thank you for coming to the class, Drew. I do appreciate it. Administrative things, I did get everything graded on chemistry. I posted the solutions for the midterm. You guys all did fantastic. And thank you for taking advantage of the extracurricular problems because it helped all three of you get those full points. There were some minor misses. Overall, conceptually, I think you guys did fantastic. I did provide some specific feedback to some of you in terms of taking that, showing the approach. Again, to reiterate, I mean, when I'm asking you to show your approach or showing the steps, it's like if there's 5 problems within one problem or 5 sub-problems within one problem, I'm not expecting you guys to kind of do it on every single one of them, but at least, take the effort to walk me through the logic and the concept with one of those sub-problems within that problem to kind of demonstrate to me that you understand the concept and show me the steps with regards to the to the logic. So I kind of commented on that. I did cut some minimal points on that, but you guys were able to make it up with the extracurricular ones. But please remember to do that in the homework and in the final exam. Otherwise, everyone did fantastic in this course. I did post the solutions, the solution key for the midterm under that drop-down menu under learning materials. Provided you individual feedback on your midterms. If you have any questions, please do not hesitate to reach out. Okay. Let's get back to the thing here. I want to finish up this chapter and then we'll kind of see where we go from this one. So share screen here. So we are going to learn the concept of, we finished equilibrium. Any questions on equilibrium, energy changes, the reaction energy diagram, or any of those things? I mean, Drew, you are the only one in the class, so feedback is completely on you, buddy. Any questions on what we learned last week in terms of equilibrium?
No, I think I'm good so far.
Okay, great. And so I'm going to build up on this one, because this is an important concept and I want to cover the Le-Chatelier's principle here. So let's go back to, so we learned about the equilibrium constant K, which is basically the ratio of the concentration of products and the concentration of the reactants, products on the numerator, reactants on the denominator, right? And then please don't forget to adjust it for the right index. Index means raised to the power based on the molar constant. So there is my little scribe here. So for this equation, the equilibrium constant is simply but K, concentration, which is always indicated by the square brackets. And since you have 2 moles on the product side, raised to the power 2, and then concentration of one reactant and concentration of another reactant, and both of them are raised to the power 1, which you're perfectly fine omitting because you have 1 mole of reactant A combining with 1 mole of reactant B to give you 2 moles of product AB. Okay, so this is how you write the equilibrium constant, which we're going to be learning moving forward and applying that. And we looked at some of these example problems of this equilibrium reaction between nitrogen and hydrogen combining to form ammonia, and the equilibrium constant for that is 200. And then we kind of learned how if K is significantly greater than 1, then the reaction is favorable to the product side. If K is less than 1, then that means you have more reactants than the products. And then finally, when K is approximately equal to 1, then you have products and the reactants in the same concentration, which is indicated roughly. This is all not exact, but roughly. Okay, so this is where we finish. And today we're going to be applying the Le-Chatelier's principle. We're going to define what is the Le-Chatelier's principle, and then we're going to be applying that for reactants. Okay, so are we good, Drew?
We're good.
Okay. So the Le-Chatelier's principle, it's a French name. I'm not sure male or female, but definitely French. The scientist who discovered this principle. And this is applicable for reactions in equilibrium, where reaction is, just to refresh, reactant or reaction rate of the forward reaction is equal to the reaction rate of the reverse reaction. So forward is this way, reverse is this way. So this means that the reactant are still getting converted to products, but the products are getting reconverted back into the reactants at the same rate, and that's what is called as equilibrium. Okay. And now we are going to see what is the effect of changing some of the reaction conditions when a reaction is in equilibrium. Okay. So I'm going to skip forward and then kind of give a sneak peek of what are the different effects that we are going to be looking. And then we're going to come back and look at most of them one by one. So first one is concentration. So if a reaction is in equilibrium, and I'm going to go with a simple reaction, sorry, A giving you formation of B. Okay. A giving you B. Okay. So what happens if you change the concentration? So concentration changing, which is indicated by any change, is generally indicated by this delta triangle. So concentration change is condition number 1. Then the next one we're going to see is changing the temperature. And the third one is changing the pressure. So changing concentration, changing temperature, and changing pressure. These are the 3 conditions we're going to be looking at, okay, for reactions in a state of equilibrium. And the most simplest way I can kind of address this is by referring you guys to this table. So this is where I want you guys to kind of bookmark this table, pressure changes. Oh, sorry. Hold on 1 second, please. Someone's at the front door. Let me just open the door and come back. Sorry about that, Drew. Okay, so we are going to be looking at the 3 conditions changing. So when you change the concentration of a reactant, the equilibrium favors the products. Equilibrium favors the reaction is going to shift to the so you have the reactants giving you products, okay, in this form. So when you change the concentration, increase the concentration of the reactant, you're going to be shifting the equilibrium to the product side. When you are decreasing the concentration of the reactant, you are going to be shifting the equilibrium to the left-hand side, which is favoring the reactants. Then when you are going to be adding products, okay, again, the equilibrium gets shifted to the left-hand side, favors the reactants. And then the 4th condition with change in concentration is when you're lowering the concentration of products or removing the products, then the equilibrium is going to be shifted to the right-hand side and favoring the product. Okay, so there is a whole bunch of slides that we will skim through, but this is essentially the gist of the 4 conditions. The simplest and most effective tool is to kind of bookmark this slide so that you can understand this is the effect of changing the concentration on the reactant side and on the product side, and which side it is going to favor the equilibrium. Then the second condition is increasing temperature. Now, because anytime temperature is involved, there is a change of heat, which is the change of enthalpy, okay, or the reaction heat. And you know that when there is a change in energy in the form of enthalpy, you have to define whether it is an exothermic reaction or an endothermic reaction. So what this Le Chatelier's principle is saying is that in an endothermic reaction, increasing the temperature favors the products or shifts the equilibrium to the product side. Decreasing the temperature in an exothermic reaction, equilibrium favors the reactants. So decreasing the temperature favors the reactants in an exothermic reaction. In an endothermic reaction, if you decrease the temperature, the equilibrium favors the product. So this is endo, this is exo. So this is decreasing temperature. And then when you increase the temperature, it is the reverse. So it favors the equilibrium under exothermic reaction, and it favors the reactants in terms of the endo. Okay. And then the last condition we're going to be looking at is changing the pressure. If you increase the pressure, equilibrium favors the side that has got fewer number of moles. Okay, so if the reactant has got more number of moles, then in this condition, so what this means is if A gives you 2B, right? So the reactant side has got fewer number of moles. So increasing the pressure, the reaction is going to be shifted towards the side which has got fewer number of moles. If the product has got more number of moles, 2A giving you PB, then the equilibrium is going to be shifted towards the product side because it has got fewer number of moles when you increase the pressure, and vice versa. So I do not expect you guys to remember all of these conditions, but it's important to understand how you apply this in a given problem. This hopefully by now you guys are getting the sense that this is more about an application course, not really a test of your memory. I've said this multiple times and you'll keep hearing me say that, just to reinforce the concept that this is a test of your ability to apply certain principles and your certain concepts that you have learned. It's not really trying to gauge whether you are able or capable of memorizing these concepts. Okay, so let's look at some examples. So in this reaction, okay, you're increasing the pressure. You have 1 mole of nitrogen, you have 3 moles of hydrogen. Okay, so totally you have 4 moles. The product is giving you 2 moles of ammonia. So a normal reaction under equilibrium, 4 moles on the reactant side, 2 moles on the product side. So when you increase the pressure, the equilibrium is driving it towards the right hand side because it has got fewer moles. Okay, so there's a whole bunch of these. I'm not going to go through all of them, but I want you to understand that every single reaction follows these general concepts according to this table. So let's look at some practical applications. In which direction is the equilibrium shifted when the pressure is increased and decreased? Okay, so this is scenario number 3 or condition number 3, change in pressure. Okay, so the table says that increasing the pressure, equilibrium favors the side that has fewer moles. So let's try to go and calculate the number of moles. So you have 1 mole of reactant 1. And again, where do you get the number of moles? You always get that in terms from a balanced chemical reaction. So the BCR or the balanced chemical equation, BCE, never goes away. Your job before you start any problem is to ensure that you're getting the confirmation that the equation is balanced. So you have 1 mole of reactant 1 plus 1 mole of reactant 2 gives you 2 moles of reactant 2 gives you 1 mole of product. So you have 3 moles and you have 1 mole. Okay, so you have less number of moles here. So increasing the pressure shifts the equilibrium in the direction that decreases the number of moles. So in this case, it's going to be shifting to the right hand side. And vice versa, once you decrease the pressure, it is going to be increasing toward the equilibrium is going to be shifting towards the number of moles that are more. Decreasing the pressure, equilibrium favors the side that has more moles. So to answer this question, when you increase this pressure for this specific reaction, equilibrium is going to be shifted to the right in the first instance. And in other words, it is going to be forming more product, okay? And in the second case, when you decrease the pressure, you're going to be shifting the equilibrium to the reactant side. So you're going to be forming more of the reactants. Let's check if that makes sense. Increasing the pressure shifts the equilibrium to the right, to the side of your moles. Decreasing the pressure shifts the equilibrium to the left, to the side of more moles. Make sense?
Yeah, I won't be that very fast at it, but yeah.
Yeah, but again, I mean, I'm not expecting you guys. I would be surprised if you picked up everything. But as long as you understand the general concept, and that's why I'm kind of trying to keep it as simple as possible in terms of, you know, these two tables. So how you apply this table is what I'm hoping that you guys pick up. And this will certainly come with more practice. And that's where the homework is there. And eventually the final exam will be there. Okay. So let's pick one more example here on concentration change, okay? So there must be a problem somewhere here. Okay, in which direction is the equilibrium shift at which each of the following concentration changes for the given reaction? So the reaction is given, so this is a different reaction, okay? 2 times SO2 plus oxygen gives you 2 SO3. Feel free to validate that this is balanced, okay? So now they're saying increase the SO2. So now learn to look at it from this reaction. R1 plus R2 gives you product. So 2 reactants combining with each other to give you a product, okay? So the first one is increasing the SO2. SO2 is a reactant, so increasing the reactant, okay? And you don't need to track it individually because it's the same whether it's SO2 or whether it's oxygen. And the second one they're saying is increasing the product. Then they're saying decreasing the reactant, and then they're saying decreasing the product. So let's go back to our matrix here. Okay, and now you're looking at condition number 1. Adding reactant, equilibrium favors the product. Removing reactant, equilibrium favors the reactant. Okay, so let's go back to our problem. I forgot which slide was it. There you go. Okay, so increasing the SO2, increasing the reactant, you are going to be favoring the product. So I would say the equilibrium shifts to the right-hand side or product. Increasing the SO3, which is increasing the product, should have a reverse effect. So now it is going to shift to the left and you're going to be favoring the formation of reactants. Let's check these 2 scenarios. Increasing the SO2 drives the equilibrium to the right to form more product. Increasing the product concentration drives the equilibrium to the left to form more reactants. Okay, and then come back here to the table. Adding product. Oh, sorry, that is something that we have already looked. And the third scenario in our problem is removing the reactant. So now you're decreasing the concentration of the reactant. Equilibrium favors the formation of the reactants. Removing the product, you're going to be shifting the equilibrium to the product side. So go back to your problem. So decreasing the oxygen, so you're decreasing the concentration of the reactant. In this case, the equilibrium should shift to the left and you should form more reactant. And decreasing the SO3 should shift the equilibrium to the right-hand side and you should form more product. So decreasing the reactant drives the equilibrium to the left to form more reactants, which is what we said. And then decreasing the product drives the equilibrium to the right to form more product. So it's simply applying those concepts to make sure that you are following the right scenario in terms of concentration change, to pressure change, and to the temperature change. In case of the temperature, before you apply those 2 scenarios of temperature change or temperature increase or temperature decrease, identify whether it is endothermic or exothermic. Okay, when temperature is increased, the reaction that absorbs heat is favored. When temperature is decreased, the reaction that releases heat is favored. Okay, so for example, and if If it is not explicitly stated whether it's a reaction is endothermic or exothermic, look for the sign. A positive sign indicates that it is an endothermic reaction, and negative sign indicates that it is an exothermic reaction. This reaction is plus 43, which categorizes this as an endothermic reaction. So when you increase the temperature according to that matrix, the reaction absorbs heat, and that's why the reaction is shifted to the right-hand side. In an exothermic reaction, when the temperature is increased, the reaction that absorbs heat is favored, and that's why the equilibrium is shifted to the left-hand side. When the temperature is increased, in both instances, the temperature is increased. Okay, one of them, it's an endothermic reaction, the first one, so that's why equilibrium shifts to the right. In an exothermic reaction, when the temperature is increased, the reaction is shifted to the left-hand side. Okay, so again, I implore you guys to kind of keep. Oh, someone texted something. Let me make sure I'm still okay with this one. Don't see anything here. Oh, that's just me texting. Okay. So those are the three conditions that I want you guys to remember from the matrix: change in concentration, which is the same as change in concentration, then change in temperature, which is delta T, and change in pressure, which is delta P. Okay. Questions, or do I have your permission to move forward?
Nope, I'm good.
Cool. All right. So there's one more subtopic I want to finish, and then we can shift to the next chapter. Body temperature. And this kind of applies what we have learned in the Le Chatelier's principle. Okay. And just to reinforce, all three conditions, change in concentration, change in temperature, and change in pressure, only for reactions that are in equilibrium. So these conditions are not applicable only when there is a forward reaction. So few things to be observant. Make sure that there is a reaction in equilibrium, which is implied by the forward reaction, reverse reaction, and always make sure that this is in balanced chemical reaction or balanced chemical equation form. Okay, so these two things, make sure this is in equilibrium, because you can't apply the change if it's not in equilibrium, and make sure that it is a balanced chemical reaction, especially when it involves change in pressure. Okay, so hopefully to the point of getting irritating in terms of me bringing this up again and again, we're again going to take recourse to the human body because it is a beautiful example of how various biochemical reactions are happening, how the microbiology is working, but there are complex organisms that are simply following the basic principles of chemical equations, which involve energy and reaction rates. Okay, and a classic example of that is metabolism. Okay, and this is hopefully not a surprise when I say that millions of reactions are occurring in the body when nutrients are metabolized and new cell materials are synthesized. We talked about it, right? So now let's look at it specifically from a Le Chatelier's principle. Normal body temperature is 37 degrees centigrade, which if you convert it should be roughly about 96 degrees Fahrenheit, give or take, might be 97. Okay, it gives you the delicate balance between the amount of heat absorbed and released in terms of reactions, which is heat absorbed is endo and heat released is exo, correct? And you already know that every reaction is characterized by energy being released or energy being absorbed. So it's that delicate balance between how much of energy is released between a certain chemical reaction and how much of energy is absorbed. Okay, now let's apply Le Chatelier's principle. So since reaction rate increases with increasing temperature, what we're trying to say is it is important to maintain the right temperature for proper body function. That's what happens when you have a fever, right? If you have too much of a energy generation, that's when your body gets extremely hot, and then that is indicated by your body temperature going down. And believe it or not, at that point, your reactions are slowing down. That's why you feel really crappy when you're feeling sick. Okay, and that's why it's important to regulate the body temperature and allow it to cool down. And let's see how that happens. This is basically the concept of thermoregulation, which is nothing but a thermostat that we all have, which nature has created for us. Okay, so there is a temperature sensor. It's nothing different than what you have in your regular home or your apartment. Okay, so let's look at this. The hypothalamus, which is the temperature control, is one of the parts of your brain. Okay, your skin has got all these sensory nerve endings which go through the capillaries, the sweat gland, and the nerves. This is not a course in biology, but these sweat glands are stimulating when the temperature increases to cool the body by evaporation. Okay, and what happens is if the sensory endings are temperaturing that there is too high of a temperature, that's when you start sweating. And that's when that sweating is nothing but your hypothalamus, which is your thermostat, telling your body, okay, the temperature is too high, I need to start cooling myself. And one way you start cooling is by sweating, which is the process of evaporation. That evaporation is nothing but a chemical change. Okay. On the other hand, when your temperature starts decreasing, your blood vessels start constricting. Okay, so when you are having a higher temperature, your body starts dilating. Dilating is nothing but your blood vessels, your veins, and your capillaries starting to expand. It releases more heat. Okay, and that's how you start sweating. The reverse is also true. When you are exposed to a chilly environment, your body starts shivering because your blood vessels are basically doing the opposite of dilation, which is nothing but constriction. And this conserves heat because as it is, you are struggling, your temperature is low. So whatever heat you have in your body, you don't want to let it go. And that's why you start constricting everything. And that's why you start shivering, which is one of the manifestations of the temperature change. But ultimately, both the dilation and the constriction are nothing but application of Le Chatelier's principle. Does that make sense?
Yep.
Okay. So hopefully this demonstrates that, again, coming back to that saying that I've been doing all along, is like everything in real life can be explained, including your basic functionality of how you're living your life day to day. Every single attribute can be explained by basic principles of chemistry. Okay. Cool. All right. We talked about all these things. So I think that's all I have for this chapter on number 6, energy changes, reaction rates, and equilibrium. So any questions?
No, I need to do my homework before I forget it all.
Yeah. Right, but everything is recorded, so you can certainly come back and revisit the recording if that helps, or if it's going to be easier, please reach out. This is telling this to you because you're here in person, but same thing for Matt and for Brian. If you guys have any questions, I'm just a phone call away. Okay, so please take advantage of that and make sure that you're reaching out, because otherwise I can't help you guys out. Okay, I'm going to close this one, and we are going to get started with chapter 7, which is going to be another long chapter. So we'll see how much we can make progress. I do intend to stop at 7 o'clock like I normally do. Do you need a break, or are you good to go for another 45 minutes ish?
Nope, I'm good. Let's do it.
Okay, cool. I appreciate that, Drew. Okay, so now we are going to start chapter 7, which is gases, liquids, and solids. There's a bunch of introductory material. I am going to be skimming through most of them because I don't want to reinforce the concept. You guys already understand what a gas is, what a solid is, and what a liquid is. Okay. But just because I'm skipping these, my goal is to see if I can get us back on track between now and Thursday. Depending on where we are on Thursday, we might consider doing a makeup class because I do want to get caught up. Otherwise, it's just going to keeps on putting us on this makeup track, which I'm not a big fan of. Okay, So we'll see where we are on Thursday, and then we'll make the final call. But I do want to again reiterate, I am going to be going a little fast today with this chapter. But if something doesn't make sense, I encourage you guys. This is one chapter where I really want you guys to kind of skim through the slide deck. And if something doesn't make sense, or you feel that I did not do adequate justice to that concept and I should have spent more time, please reach out. If you don't, then I'm going to just make an assumption that you guys have understood the concept. So forgive me for taking that position. Okay. So chapter objectives: measure pressure and getting converted from one unit to the other. We are going to be fundamentally operating within the regime of interrelationship between pressure, volume, temperature, and number of moles of gas. Okay, so you know pressure concept. Pressure is nothing but force per unit area. Volume is how much space a certain entity occupies. And you know that gas occupies the most, liquid occupies somewhat in the middle, and solid occupies the least. Always think about water, which exists in the form of ice, which is solid, water in the liquid form, and gas in the form of, water vapor in the form of gas. Okay, to kind of keep things in perspective. Okay, so we are going to be learning about the interrelationship of this, and that's where I'm going to start off. I'm going to start straight with the ideal gas law, and then we are going to work our way backwards, because then there is a relationship between pressure and volume. There is a relationship between volume and temperature, and then there is a relationship between temperature and pressure. Okay, but if we learn the ideal gas law, and as the name suggests, okay, the ideal gas law is under ideal conditions, okay, standard conditions, which we're going to be defining here. So once we learn the ideal gas law, which basically correlates these four parameters with a constant called capital R, okay, that should allow you to address this one, and this one. Okay, so we're going to be learning about ideal gas law, and in the interest of time, I'm going to be working our way backwards and just expose you to the ideal gas law, and then come back and individually address the other gas laws between volume temperature relationship, pressure volume relationship, temperature pressure relationship. Okay, and then we are going to learn about Avogadro's law, which is where we are defining this R value. Okay, so that's one of the objectives of this chapter. And then we are going to be learning Dalton's law. So this is a bunch of relationships, which is what you mean by when you say the word law. Okay, so Dalton's law is basically how the partial pressure is related to the total pressure of a gaseous mixture. Okay, and as the name suggests, partial means something that is not complete. So if you have a gas that is comprised of A plus B plus C, okay, and this is a mixture, what this is saying is the pressure of each of these individual components is equal to the total pressure that is exerted by the gas mixture as a whole. So if I'm representing gas A with these things, which is, let's just call it blue color, right? And then yellow would be gas particles B, and then let's go with black for gas particles C. Okay, so what this is saying is the pressure of the individual components of that mixture, you take those and add those up, and basically that's going to be equal to the total pressure exerted by this gas mixture system. That's what Dalton's law is saying. So a good portion of this chapter is actually going to be focused on gaseous mixtures, and gases are what you would call, believe it or not, are called as compressible fluids. Have you heard this term, compressible?
I mean, I could put the two words together and figure it out.
Yeah. Because liquids, on the other hand, are incompressible fluids. And what that means is you cannot compress them, right? Take this thing, I mean, when you take a pump, right, and try to inflate a balloon, what are you trying to do? You're taking a gas and compressing it, right? That's what you're compressing it. Imagine that gas is full, that air that you're there in the living room is basically filling up that whole space. You're taking some of that air and forcing that into a finite volume of that balloon, right? And as that volume expands, the balloon expands, you know that you're increasing the pressure, right? Can you correlate this concept?
Yeah, but I mean, when you go deeper into the ocean, there's more pressure.
I agree, but that's, and you're absolutely correct, but that's, I'm not saying that the pressure doesn't increase, but I'm just saying that the pressure, when you're going deeper into an ocean, Drew, you're absolutely correct, it increases, but the water does not change its shape, right? The water is still maintaining that same volume in terms of where you are in that ocean. If you're deeper, now you just have a higher water column exerting that pressure. But in the case of gas, you're actually taking a gas and then compressing it and changing its volume. Do you see the difference?
Yeah, I'll go along with it. Yeah.
Yeah. So that's the definition, a key difference between compressible fluids. And for some reason, gases are considered fluids. And the reason for that is because gas flows. So in a pipeline, you have natural gas, right? Or you have air, right? Or you have oxygen. If you go to big production plants, chemical process industries, you have these fluids that anything that flows is deemed as fluid in the fluid world. Okay. The only difference is that gas can be compressed, where you can apply some pressure and change the volume. That's the definition of a compressible fluid. And liquids, on the other hand, when you apply the pressure, you're not changing the volume still remains the same. Okay. So we're going to spend some time on compressible fluids, compressible fluids as the focus of this. That's where this whole concept of ideal gas law, Charles' law, Boyle's law, and there is one more I'm forgetting that. We'll look into that. That's a relationship between these four entities for a given volume of gas, or given what's the word I'm looking for? Given quantity of gas. Okay. And then we're going to spend some time about the properties of liquid, and then we'll talk very briefly about the different types of solids, especially the specific heat. But by and large, if we can focus on the literally, I think I might spend maybe 45 minutes between today and Thursday to finish up the liquids and solids. Bulk of it is going to be focused on gases. Okay. So we have already looked at the three states of matter. I'm going to just simply skip through all of these. The gas has the kinetic energy. That's why the particles are far apart. We kind of covered all these things in chapter 1. That's the reason why I'm kind of taking the liberty to kind of not going through the reiteration part, just so that we can save some time. I encourage you guys to kind of read these slides just so that you're getting caught up in terms of the concept we already learned in the beginning part of this course. So if you remember, we had looked at chapter 1, where we introduced properties of gas, shape and volume. Gas expands to fill the container. Liquid takes a fixed volume, it takes the shape, but doesn't fill up the container. Solid doesn't take a shape or volume. You put a pebble in a jar. It doesn't matter how big that jar is. The pebble is always going to be holding on not only its shape, but its volume. Okay. Whereas a liquid, you put that thing over here, it will take the shape of that, but it will not have a finite volume. Gas, it pretty much takes this whole space. Okay, and then there's some other characteristics, arrangement of particles in terms of the kinetic energy, the particle movement, interaction between. So these are some standard characteristics. The density, gases are the least dense. Density is nothing but how much a certain entity weighs. In terms of, and again, we are not talking in terms of acceleration due to gravity. It's the mass divided by a given volume. So if you take a given volume of, say, 1 liter, A solid is going to be the most dense because it is going to be having the most compactness. Liquid is going to be somewhat in the middle. Okay. Oh, sorry. It's going to be somewhat in the middle, and yeah. And then gas is going to be the large. No, I got this completely wrong. Sorry. So for a given volume, say 1 liter, solids is going to be the most dense because it has got the least amount of volume. So given for the same amount of mass, where did my presentation go? Okay, so say you have 1 kg, right? So 1 kg is having the smallest amount of occupancy, so it has the highest density. Solids, then liquids have the medium density, and then gases have the least density. Okay, think about it. You have a stone, you have a balloon filled up with helium. Which one is going to be lighter? Then lighter means the opposite of dense, right? And density is the absolute term how you measure how dense or how light it is. Okay, but in terms of heaviness, for a given volume, you know that the gas is going to be the least dense. That's why it's going to be the most lighter. Okay, so gases and pressure. We looked through most of these things. Let's see what we want to kind of pick up from here. Pressure from your basics physics course is nothing but force per area. There's a whole bunch of units to measure pressure. And the instrument that is used to measure the pressure is called as barometer. Okay, it is nothing but this simple device where there is a mercury, okay, filled dish. Mercury is your element Hg from the periodic table, and this is the only liquid metal. So this mercury has got a very unique property, both in terms of pressure and in terms of temperature. When it is used as a barometer, which is basically a device for measuring the atmospheric pressure. What is atmospheric pressure? Is the pressure that the atmosphere exerts on us. You have heard the saying that in Colorado, the air is thinner. Have you heard this?
Yep.
Okay, so compare that. So we are at 5,000 feet elevation, roughly, give or take, in Colorado. Compare that to the sea level, which is take either California or Florida. So the air, because it is thinner, exerts a lower atmospheric pressure in Colorado compared to the same air, which is exerting the atmospheric pressure at sea level. So this sea level atmospheric pressure in terms of millimeters of mercury is 766 millimeters. What this is saying is, if you take a barometer and take it to Florida, you are going to, this pressure is, the atmosphere is going to be exerting this pressure. The way this barometer is designed is that it is going to be putting this mercury inside this tube. And if you read it for mercury, you will see that it will measure 760 millimeters in Florida. And the same thing, because it is lighter here in Colorado, it will measure, I need to find this out, atmospheric pressure in Colorado Springs. Let's be more specific. It is 31.6 inches of mercury column. Now we need to convert it from inches to millimeters. 1 inch is 2.54 centimeters, and doesn't make sense. Why is it coming half Colorado high pressure or low pressure? inches. Okay, something is a little confusing here. .16. Okay. You guys, you get the idea, right? I'm not able to give you the exact thing that I was, but you understand that because the air is thinner, the Colorado atmospheric pressure is going to be lower compared to what it is in the sea level. Would you agree with that?
Yep, got it.
Okay, all right. I don't want to spend too much time on this. Okay. Okay. Now, again, this is a slide number 26 that I would probably bookmark, but you can always use the internet as a resource. This is just converting it from one unit to the other. The most commonly used unit for pressure is atmospheres, okay? And 1 atmosphere is equal to 766 millimeters of mercury. It's also 760 torr, which is named after the scientist who discovered that 1 millimeter of mercury is what is defined as the standard unit of pressure. So in honor of that individual, they named it torr, okay? So it's important to just understand here in the US, since we are not using the metric system, the metric system uses atmospheres. We use pounds per square inch, which is what you're most familiar with in terms of your air pressure in vehicles and in your bikes, and also in your water pressure coming in the taps. So 1 atmosphere is equal to 14.7 psi. And then another unit is in honor of another scientist who did a bunch of measurements related to pressure. And that gentleman's name was Pascal. And 1 atmosphere is also equal to 101,325 pascals. Or also, since this is a large number, you can go with 101 kilopascal. Okay. Again, the intent is trying to be flexible and understanding that pressure can be measured in different units, just like any other entity. So there are some basic problems here. A scuba diver typically begins a dive with a compressed air tank at 3,000 psi. Convert this value to atmospheres or millimeters of mercury. Simply 3,000 psi. Divide that by 14.7 to get it in terms of equivalent atmosphere. So you'll get 3,000 times 1 atmospheres over 14.7 psi. PSI gets canceled, you get 204 atmospheres. When you're converting that in terms of millimeters of mercury, you know that 14.7 psi is equivalent to 760 millimeters according to this conversion table here. Okay. And then when you apply that to the problem, you get 155,000 millimeters of mercury. It's again manipulating one unit into another using the right conversion factor. Okay. Let's talk about blood pressure. We have all taken this at every single doctor examination, physical examination that we go to. The instrument is basically a sphygmomanometer. Okay, that's the device that they use to measure the blood pressure. It has got the higher number is always the systolic pressure. Okay, and it measures the maximum pressure in the artery after the heart contracts. The lower number is the diastolic pressure. And a normal healthy person is expected to have blood pressure in the 100 to 120 on the top side or the numerator, and the denominator is 60 to 80. Okay, and anything outside of this, you call them as hypertension or high blood pressure, or you call them as having low blood pressure. Neither of them is a good sign. Okay, so this is what it does. Okay. All right, so now let's get into the gas laws. I'm going to be skipping through some of these. Boyle's law is the relationship between pressure and volume. Okay, we're going to come back to this. Okay. Then Charles' law is the relationship between volume and temperature. Okay. And there is one more here. Gay-Lussac's law. These are two individuals. This relates the pressure and temperature. Okay. So what this says is Boyle's law says that as pressure increases, I would certainly bookmark this one, and which is also that all three of them are together called as the combined gas law. Okay. And the combined gas law tells the interrelationship between pressure, volume, and temperature for any gas. And in a nutshell, what the three laws are, the combined gas law, as the name suggests, is a combination of these three: Charles' law, Boyle's law, and Gay-Lussac's law. Okay. So it's a combination of all three, and it gives you the interrelationship between the three characteristics or three parameters for any given gas. Okay. Boyle's law says that as pressure increases, the volume decreases, or in other words, mathematically, the pressure is inversely relationship. It has an inverse relationship for volume at a constant temperature. That's the thing that you have to remember. When you're doing the Boyle's law, the Charles' law, the Gay-Lussac's law, two of the parameters are getting affected at the expense of the third one being constant. For example, you take a gas, you start compressing it. Think about it. You apply pressure externally, that volume is going to decrease. So that's why pressure is inversely relationship to volume, or mathematically you can say that the product of pressure and volume is always equal to a constant, which can be then further interpreted as, if you have an initial condition and a final condition, which is indicated by 1 and 2 respectively, you are seeing P1 V1 is equal to P2 V2. Or in other words, a low pressure here and a high volume is the same as a high pressure and a low volume. Okay, so this is Boyle's law, which basically states a relationship between pressure and volume at a constant temperature. Charles' law is the exact same thing, but the relationship between volume and temperature at a constant pressure. We'll come back to the number of molecules n, okay? But what the Charles' law says that as the temperature increases, the volume increases. This is actually very easy to imagine intuitively. Apply heat to anything. Most of the times you will see that the volume of that starts increasing. Okay, so what this is saying is volume is directly proportional to temperature, and that's why volume over temperature is a constant. Or in other words, V1 over T1 is equal to V2 over T2. And Gay-Lussac's law says the exact same thing, but now the relationship is between temperature and pressure. What this is saying is as you increase the temperature, the pressure increases. Or in other words, T over P is constant, or T1 over P1 is equal to T2 over P2. Or vice versa. You can also say P is directly proportional to T, which says that P over T is constant. Or you can say P1 over T1 is equal to P2 over T2. And we're going to look at some examples where we're going to start applying these, and then that will start making sense. Okay. So again, you don't have to memorize this. Again, keep in mind, that this is the relationship, this is the relationship, and this is the relationship. And obviously, the combined gas law is taking all three of them and combining together. And that's why you get P1 V1 over T1 is equal to P2 V2 over T2. So the combined gas law says P1 over T1 is equal to P2 V2 over T2. Okay, if you keep the temperature constant, then it becomes P1 V1 is equal to P2 V2, because T1 is equal to T2, correct? And P1 V1 is equal to P2 V2 is nothing but your Boyle's law. Okay, then if you do this thing, if you keep the pressure the same, then you get V1 over T1 is equal to V2 over T2, because pressure is the same. So P1 and P2, the 1 and 2 just indicate that they're initial condition and final condition. Okay, so V1 over T1 is equal to V2 over T2 is nothing but Charles' law. Let me check that. V1 over T1 is equal to V2 over T2, correct? And then the third condition is, you erase this one, and you say that the volume is the same. So P1 over T1 is equal to P2 over V2, because the volume is the same. So V1 is equal to V2, or volume constant. And this is nothing but the Gay-Lussac's law. P1 over T1 is equal to P2 over T2. Okay, so there's a whole bunch of things. Now I want to kind of indicate some things in terms of an application. Okay, most of them you should be able to attack. There will be a whole bunch of problems related to this chapter in the homework, and also the final exam. Okay, one very important thing to understand here is that the temperature, and this is mentioned somewhere over here, is the temperature unit has got to be in Kelvin. Okay, if you remember chapter 1, we had defined 3 different scales for temperature: degrees centigrade, degrees Fahrenheit, and degrees Kelvin. Okay, how do you get to degrees Kelvin? You add 273. So if your temperature is given in degrees centigrade, which is 37, to degrees Kelvin would be 37 plus 273, which would give you 310. All of the gas laws only work when you use the temperature scale to be in Kelvin. That's very, very, very important. The volume and pressure, you can use it in any other units that you prefer, but temperature has always got to be in Kelvin. Okay, let's go back and apply some of these things in terms of the problems. Okay, so Boyle's law is pressure and volume, temperature constant, so you don't even have temperature in here. You don't have to worry about temperature. What this is saying is PV is equal to constant, or P1 V1 is equal to P2 V2. Okay, so this is the graphical illustration. You take a piston and you compress this gas. Originally, you have a pressure of 1 atmosphere and the volume is 2 liters. When you apply it, you're compressing it, the pressure increases and the volume decreases. Okay, that's why PV is constant, okay, or P is inversely proportional to volume. Okay, so let's look at a problem. If a 4-liter container of helium gas has a pressure of 10 atmospheres, what pressure does the gas exert if the volume is increased to 6 liters? So always with any problem, start out with documenting what you have. Okay, so you have V1 is equal to 4 liters. P1 is equal to 10 atmospheres. What pressure does the gas exert? So P2 is unknown, and volume 2 is given to be 6 liters. Do you understand, Drew, how I came up with how I converted the word problem into 4 values and assigned them variables: V1, P1, V2, and P2?
Yeah, I think so.
Okay, so always start with baselining every problem and convert it from a word problem to an equation, not equation, to values. So these are all the three things that are given. And this is what you are going to be finding. Okay, now the equation is P1 V1 is equal to P2 V2. You're required to find P2, so isolate it. P1 V1 over V2, plug and chug, and you should get 10 atmospheres, 4 liters, 6 liters, the liters and liters. If you set up the equation correctly, the liters should get cancelled and you should only be left with the right unit, which is what you need the answer. Which makes sense because according to Charles' law, if you are going from, where is the problem again? So 4 liters and 10 atmospheres, you're going to a higher volume, so pressure has to decrease. So you know that intuitively the second pressure, the P2 that you're calculating, has got to be a lower pressure, which is what it is in terms of the answer, 6.7 compared to 10. Okay. So that was Boyle's law. Okay. Tank of compressed air for scuba diving, okay, contains 8.5 liters of gas at 204 atmospheres. So that same cylinder, when you reduce the pressure to 1 atmosphere from 204 atmospheres, that's a significant decrease. You're reducing the pressure significantly, so you know that the volume has to expand significantly, correct? Intuitively. But let's look at the answers. So V1 is 8.5, P1 is 204, and P2 is 1 atmospheres. You are required to find V2. What volume of air does this occupy? So again, P1 V1 is equal to P2 V2. V2 should be P1 V1 over P2. Simply substitute, and you should get a significant increase in volume. 1,734 rounded up to 1,700 liters. So compared to the original volume of 8.5 liters, now you're occupying 1,700 liters because the pressure decreased. So this is Boyle's law. Okay. Boyle's law can also be used how the human body exhales and what's the opposite of exhalation? Inhales and exhale. So our normal respiration process, when your rib cage is expanding and contracting, can be explained because you're inhaling air, so the pressure increases because everything is getting pushed out. When you're exhaling, the volume is reduced, and that's why the lungs collapse or the rib cage collapse. Okay. Charles' law, keeping a relationship between volume and temperature, the pressure is constant at constant pressure. Okay, since you are dealing with temperature, always make sure that the volume of the gas is proportional to its temperature in Kelvin units. This is, if you forget to do the Kelvins, I promise you, you'll lose the you'll get the answer wrong. Okay, let's apply the formula. So this is the graphical representation. Okay, I want to go directly into a problem. A balloon that contains 0.5 liters of air at 25 degrees centigrade is cooled to negative 196 degrees centigrade. What volume does the balloon now occupy? So this is V1, this is T1, this is T2. So now when you are required to calculate the relationship between volume and temperature, you know it's Charles' law. You know that V1 over T1 is equal to V2 over T2. Okay, V1 over T1 is equal to V2 over T2. The important thing to understand and remember is T1 and T2 needs to be in degrees Kelvin. How do you get 25 degrees centigrade? It's nothing but 25 plus 273, which is equal to 298 degrees Kelvin, and negative 196 plus 273, whatever that math is, I'm not able to do that in my head. You're going to get 77 degrees Kelvin. Okay, so this is positive 77 degrees Kelvin. Now you convert T1 and T2 to the right units. Now you can apply the ratios. and you're required to calculate V2, which is nothing but V1 over T1 times T2. So you take this and put it in the numerator. So V1 is equal to 0.5, T2 is 77, T1 is 298. And when you solve this, you will get the answer to be 0.13 liters. Okay. So when the, where is our problem here? So when the temperature is cooled from 25 degrees to 196 degrees, what this is saying is that the volume is directly proportional to temperature. So if the temperature drops, the volume drops. If the volume drops, the temperature drops. Fairly simple, right?
Yep.
Okay. So that covers Charles' law. And the third one, Gay-Lussac's law, is exactly the same. So this is another practical application of how the Charles' law explains wind currents. If you guys want to read through this, but it's exactly the same concept. As the temperature rises, the volume increases, and that's why hot air expands and it starts rising to the top, and cool air is heavier, it comes to the bottom, and that's how you get the wind current. Okay, but this is a direct application of volume is directly proportional to temperature. As you raise the temperature of the air, the volume of the air increases, and that's why lighter air starts to go up, and it's replaced by cooler air. Okay, and the Gay-Lussac's law is exactly identical. Now it's a relationship between pressure and temperature at a constant volume. Somewhere in here it should say constant volume. Okay, so pressure is directly proportional to temperature. When pressure increases, temperature increases. When pressure decreases, temperature decreases. When temperature increases, pressure increases. When temperature decreases, pressure decreases. Or you can say P1 over T1 is equal to P2 over T2. Or T1 over P1 is equal to T2 over P2. Make sure temperature is again accounted for in degrees Kelvin by adding to 273. Let's look at an application and then we can call it a night tonight. Tire on a bicycle stored in a cool garage at 18 degrees centigrade has a pressure of 80 psi. So most of our garages are kind of lower temperature compared to the outside temperature. Okay, so say if a garage is at 18 degrees centigrade and has a pressure of 80 psi,
We got no audio.
Drew, can you hear me?
Yeah, I can hear you now.
Okay, hold on. Sorry about that. Oops.
You got an echo over there.
Yeah, okay. No, my phone died. I wasn't keeping track of it, and that's where I was getting my audio and video. I don't know at what point I cut off. Can you remind me again? And hopefully we're still recording here.
Yeah, we went right into a practical explanation.
Yeah, I think, I mean, we started this bike problem, right? The temperature and this example of shoot, where did it go?
Yeah, we got through that last law.
Yeah. And what I was saying is that, oh, I think I finished it. So do you understand how we walk through the example of the
Yep.
pressure of the air that you fill in a bicycle that is
Yep.
stored in a cool garage? Did we walk through that example? And at this point of calculating 87 PSI, did
Yep,
we cover
right there.
that? Okay.
Yeah, that's where we were.
And that's where I was going to say, that's why in the summertime, it is generally said that you should not be inflating your tire pressure all the way to the top, because as you go outside, right, when you take your car outside, and through the course of the day, as the temperature increases, the pressure increases, correct? And if you start off with a very high pressure, then there is the risk that your tire may burst, because if the temperature goes crazy high, then the pressure can increase the rating of the tire pressure that the tire is rated for, and it can burst. Right? So that's basically a direct application of the Gay-Lussac's law. Make sense?
Yep.
Cool. Awesome. So I want to stop here, and I would suggest that basically we'll pick it up from here and run through the Avogadro's law. Okay, so we have finished the it's basically the inner relationship between pressure and volume, keeping the other parameter constant. And now when all three conditions are changing, they're going to be basically the combined gas law is nothing but if you have three things changing, PV and T1, you need to know at least 5 parameters to be able to calculate the sixth one. Okay. And a classic example here is this one. So identify, so right here, a weather balloon contains 222 liters of helium at 20 degrees centigrade and 60 millimeters mercury. What is the volume of the balloon when it ascends to an altitude? So as you go higher and up in altitude, when the temperature is negative 40 degrees centigrade, and the pressure is 540. So you know that as you're going up, the air is cooler and lighter. That's why you have 540 at a higher elevation compared to 760. So this is nothing but V1. This is nothing but T1. This is nothing but P1. V2 is what you're required to find. This is nothing but T2, and this is nothing but P2. So apply P1, V1 over T1 equal to P2, V2 over T2. Do not forget to change the temperature to kelvins. When you do all of those things and plug in chug, you should get, as always, make sure that you're listing out all the known entities and then what is your unknown entity. Okay, convert it into temperature, the right temperature. So original 20 degrees centigrade is nothing but 293. Negative 40 is 233, right? Then isolate the one that you want, rearrange the equation, plug in chug, and make sure that the units are consistent in kelvins, and you should get 250 liters. I know I went a little fast there, but are you able to keep up?
Yeah, I mean it's pretty simple. I mean,
yeah. Okay. So, and this is going to be the bulk of it. We have already done most of the hard work, and now we're just going to introduce one more concept where the number of moles, which is already something that you guys know. I mean, like number of moles is what we use to track the equation. And then what we are going to do is find out the relationship between volume and number of moles. And then we are going to extend it into the ideal gas law, IGL. Okay. And then we should be able to do Dalton's law and then wrap up the chapter. So I have a feeling that if we are a little aggressive on Thursday, we should be able to wrap it up on Thursday.
Okay.
Sound good?
Sounds good.
Cool. So be prepared mentally to go stay a little bit longer than what you normally stay back, because I do want to finish up on chapter on Thursday if possible. That way we don't have to do a makeup class, which I think you guys will appreciate. Awesome. Any questions, please reach out. Anything related to, if you feel that you have been unfairly graded, please let me know. If you feel you got a question wrong, I highly encourage you guys to walk through the solution key and see where you went wrong. And if you want to understand some concept, or if you think it doesn't make sense, please reach out. Bottom line is, anything you need assistance with, unless you let me know, I cannot help you guys. So please take advantage of it and just reach out, whether it's a homework problem, a discussion board, some concept that did not make sense, or anything else chemistry related.
Sounds good. I appreciate it.
Take care, Drew, and I'll see you on Thursday.
Yep. Thank you. Bye.
Bye.